is torque on a current carrying coil in uniform magnetic field. Let's take this rectangular coil. It's carrying some, this is carrying some current I in this way. And this is your magnetic field. Though the calculations are easy, but directions are very much involved in this calculation. So before starting this calculation, let's name this coil as ABCD. But you should at least know how this coil is placed. So this coil is placed. Yeah. So if this is the rectangular coil, I can place this, and this is the magnetic field. This pen is my magnetic field. So magnetic field is along x-axis. And if I place this coil in this way, like in YZ plane, exactly in YZ plane, that would mean that coil is perpendicular to the magnetic field. Right? I'm not placing the coil perpendicular to the magnetic field. Rather, I am placing the coil in this way. This is inclined at magnetic field at some angle theta. If you look at in from the bottom, then there is some angle between the coil and the magnetic field. So I'm repeating again, this coil, if I place in this way, that means your coil is perpendicular to magnetic field. Your magnetic field is along x-axis. I'm not placing coil in this way, rather I'm placing this coil in this way. This is tilted with respect to magnetic field. This angle is theta. This angle is theta. Theta is the angle between plane of coil and magnetic field. So the angle between plane of coil and magnetic field is theta. Next, we can calculate. Now, to calculate torque, the first step is to calculate force on each of the straight segment. Let's take that length of this segment is B and of this segment is L. Let's first calculate force on section AB. So on AB, the expression of force is FAB, which is I. I'm using the same expression that we have derived yesterday, IL cross B. B cross B. Now see, this is the direction of current, means this is the direction of B and this is the direction of magnetic field. And the angle between them is, if this is theta, then this angle is 180 minus theta, right? This is a straight line. If I say this is theta, then the remaining angle would be 180 minus. So your FAB comes out to be, it's I, B, B, sin theta. Not sin theta, sin 180 minus theta. Now, if you have mathematics, then in trigonometry, you must have read that 180 minus sin 180 minus theta is equal to sin theta. So if I substitute this value here, then FAB comes out to be IBB sin theta. The next step is for direction. See, this is the coil. Hold your notebook in this way. The way I'm holding this sheet, just hold your notebook in this way. Your current is coming outwards. So take your right hand, place your fingers in the outward direction in this way and curl it horizontally. Place your finger outward and curl it horizontally. Your thumb will point upwards. If I come to side BC, then this is current is I. The length of the BC is
the
yes.
AD length, the current. So what about this?
What? Sorry. AB, yes. The current passing through the AB length is I. I didn't get your question. Sorry, I didn't get your question. Please repeat. Yes. So the force on this BC section is IL cross B. Now see, L and B are perpendicular. They are perpendicular to each other. So you can write FBC is see, they are perpendicular ILB sin 90. Now if I apply right hand thumb rule, say the current is coming downwards. So take your right hand, place your finger in downwards direction and curl it horizontally. Place your finger in downwards direction and curl it horizontally. Your thumb will come outwards, out of the plane. So the direction of force on this BC section is ILB. Out of the plane of board means K cap. Just check it once. This is your coil. Current is coming downwards now. So place your finger in the downwards direction and curl it horizontally along x-axis. Your thumb will come out of the screen. Are you getting it? For this BC, your thumb should come out of the screen. Jubena, Fatma, Froza. Froza. So that's ILB K cap. Let's call this as equation number 2 and this is equation number 1. Similarly, we can calculate force on the section CD. On CD, this is I. The length of the CD is B, basically, its breadth. B cross B. So FCD is IBB sin 90. So that is FCD, which is IBB sin 90. Not sin 90, this is sin theta. If I apply right hand thumb rule, then the force will act on this section in downwards direction. See, place your finger in this way, it's going into the plane of screen and then curl it horizontally. Your thumb should come in downwards direction. Place your finger into the plane of your screen and then curl your finger horizontally. The thumb will go downwards. So force will be downwards. Downwards means minus of theta. That's equation number 3. Similarly, you can calculate dA. This angle is again 90 degree. FDA is, it's I L cross B. So that's ILB sin 90. And if I apply right hand thumb rule, then your current is upwards, your magnetic field is horizontal, thumb is going inwards. Inwards means minus of K cap. Your FDA is minus of ILB K cap. That's equation number 4. Now, next calculate net force. So if I calculate all forces, so Froza, you're getting 0 now? It's IBB sine theta j gap plus ILB k cap then this is IBB sine theta j cap, then this is minus ILB k cap. So this gets cancelled out with this thing, this gets cancelled out with this thing, this is equal to 0. This is net force, which is 0. Now this result we have calculated for the coil only, for a rectangular coil, but this result is valid for coils of any shape and size. So you can write this as net force on a current carrying coil, current carrying coil in uniform magnetic field is 0. And this result is valid for coils of all shape and sizes. This result is independent of shape and size of coil. So this is true for coils of all shape and sizes that net force is 0. If net force is 0, that means your coil is in translation equilibrium. That means you can say that your coil is in translational equilibrium. That means your coil is in translational equilibrium. After force, the next thing is we can calculate torque acting on the coil. See, for calculating torque, we need two equal and opposite forces. See, here you have two pairs of equal and opposite forces, one FAB and FCD. Another is FBC, which is acting outwards. And then this FDA, which is acting inwards. This is acting outwards. This is acting inwards. So you have to check out of FAB, FCD and FBC, FDA, which pair can rotate this coil. Can FAB and FCD can rotate this coil? Is it possible that FAB and FCD can rotate this coil? FAB is acting in upwards direction. FCD is acting in downwards direction. Can these two forces rotate this coil? We are calculating torque. See, FAB and FCD are collinear pairs. Collinear forces. Collinear forces means forces which are acting in same straight line. Here FAB and FCD are collinear. They're acting in same straight line. They don't contribute to torque. They don't contribute to torque. But if you look at this FBC and FDA, these are like, this is your coil. One force is acting inwards, another is acting outwards. One is acting inwards, another is acting outwards. So this can rotate. So these two pairs, like these two forces, FBC and FDA, can contribute to torque. They can contribute to torque, FBC and FDA. They are not collinear, they are non-collinear, they can contribute to torque. Now, I can draw this FDA and FBC in this way. Say FDA is acting in inverse direction. So this is FDA, which is acting in inverse direction. This is FBC, which is acting in outwards direction. Just for the sake of clarity, instead of representing them by dot and cross, I'm just drawing this full side. This is side CD. A force FBC is acting on CD in the outwards direction that I am drawing in this way. This is acting in outwards direction. Then this force FDA. Sorry. So this is FBC, which is acting in outwards direction. This is FBC. And this is FDA, which is acting in inverse direction. So instead of drawing FDA inwards, I'm drawing it upwards. And instead of drawing this FBC outwards, I'm drawing it downwards. And this angle with the horizontal is theta. This side is theta. Okay, just check from the previous calculation. Does FBC and FDA have equal magnitudes? Please check from the previous calculations. Does FBC and FDA have equal magnitudes? Okay. So we can write this as like FBC and FDA makes a couple. So in mechanics, couple means two equal and opposite forces which can rotate the body. In case of a couple, you can calculate torque as the product of any of the force multiplied by distance between line of action. Distance between line of action. Okay, so to calculate torque, I just write this as torque is force. You can take any magnitude of any of the force because both FDA and FBC have same magnitude. Take magnitude of any of the force. I take magnitude of FBC multiplied by distance between them. So this is line of action of first force. This is line of action of second force. Distance between both the line of action is this. I call this as N and this is point C. So this is the perpendicular distance, which is Cn. I call this as equation number 6. You know how much is FBC. We calculated FBC in equation number 2, I think. From equation 2, FBC is ILB. That is equation number 7. Similarly, you can calculate your CN. I don't need this diagram. For CN, let's use this triangle in triangle CND. How much is sine theta in this triangle? In terms of sides. Sine theta is perpendicular, which is BN, by hypotenuse, which is CD. So sine theta is not useful. Sine theta is not very useful. Instead, let's use cos theta. Yes, cos theta is Cn over CD. CD is B, so this is Cn by B. So your Cn is B cos theta. This is equation number 8. Next, what you can do is you can just substitute all values in this equation number 7. I'm substituting 6 and 8, not 6 and 8, 7 and 8 and 6. 7 and 8 and 6. So if I substitute all values here, then this torque will be FBC is ILB and Cn, which is B cos theta. Okay, can you tell me how much is this L into B? L into B, area of the coil, yes. So the torque comes out to be IAB cos theta. So if coil have n turns, so how much would be torque if this coil have n turns? Yes, we will simply multiply it with n. Yes, we will multiply it with n. So if you multiply it with n, then your torque comes out to be NIAB cos theta. So how much is NIA? You remember what is NIA? Does anyone remember what is NIA? Ah, very good. M, which is magnetic moment. Yes, this is magnetic moment. Good. So instead of NIA, if I substitute M here, this comes out to be MB cos theta. Just tell me one more thing. What is direction of magnetic moment? I've written somewhere something about direction. Is direction of magnetic moment in the plane of coil or is it perpendicular to the plane of coil? What is the direction of magnetic moment? If I take this coil, then magnetic moment is, yes, is perpendicular to plane of coil. Okay. So if you want to check, this is horizontal. This is the plane of coil. Let's call this as equation number 9. This is plane of coil. And this is the horizontal direction. You can say this is your magnetic field. What is the angle between plane of coil and magnetic field? How much is this angle? How much is this angle? theta. Magnetic moment, you said that magnetic moment is perpendicular to the plane of coil. No, Joanna, it's not 90 degrees. It's theta. The angle between plane of coil and magnetic field is theta. But you said that magnetic moment is perpendicular to the plane of coil. That means your magnetic moment should be in this direction, right? This is 90 degrees. Angle between plane of coil and magnetic moment is 90 degrees. Okay, now tell me how much is this angle? Let's call this angle. I name this as alpha. So if I add theta and alpha, I would get 90 degrees. So I can further. So I can write this as theta plus alpha is 90 degrees. What is alpha? Or you can write theta as 90 minus alpha. Let's call this as equation number 10, where alpha is angle between magnetic moment which is perpendicular to plane of coil and magnetic. This is it. This is alpha. Magnetic moment which is perpendicular to plane of coil and magnetic field. That's alpha. Now you can do one thing. You can substitute 10 in 9. When you substitute 10 in 9, you will get that your torque is mb cos 90 minus alpha. Here, cos 90 minus alpha. What is cos 90 minus alpha? How much is cos 90 minus alpha? Cos 90 minus alpha is sin alpha. Cos 90 minus alpha is sin. So this is torque, which is mb sin alpha. That is equation number 11. So if you place a current carrying coil in a magnetic field, then you should always remember that net force on the coil is 0. This coil can experience a torque which is given by m cross mb sin theta, which is mb sin alpha, or you can write this as the cross product of m cross b. Now, if you remember chapter number 1, we have done similar calculations with electric dipole. Net force on the electric dipole was 0. The torque acting on the electric dipole is Pe sin alpha or Pe sin theta. The results are same. Instead of the electric dipole moment, here we are using magnetic dipole moment. Instead of electric field that we have used in chapter number 1, we are using magnetic field. Case 1. Now we have some special cases here. The case 1. If magnetic moment is parallel to magnetic field, in the last section, I discussed two angles. One theta, another is alpha. Which one is 0 here? What is the value of alpha here? In the last section, we have discussed two angles. One theta, another is alpha. What is the value of alpha here? This is magnetic field. and I'm saying this is magnetic moment. If M is parallel to B, that means your alpha is 0 degree. Your alpha is 0. But if I look at the plane of the coil is perpendicular, which means theta, which is 90 minus alpha. So theta, which is 90 minus 0, is 90 degree. Though we have written all relations of torque in terms of alpha, but always remember the relation between alpha and theta, that theta plus alpha is 90 degree. So if I'm saying that magnetic moment is parallel to magnetic field, that is plane of coil is perpendicular to B. Because in questions you never know. He can give question in this way, or he can write that magnetic moment is parallel to magnetic field, or question could be given in this way, that plane of coil is perpendicular to magnetic field. So either your alpha is equal to 0 or your theta equal to 90 degree. Now if I calculate torque, the torque comes out to be mb sine 0. Your torque comes out to be 0. Your torque is 0, and in uniform magnetic field, net force is always 0. That means your coil neither can rotate nor it can move in a straight line. You can say that your coil is in equilibrium. Your coil is in equilibrium. So net force on the coil is 0. That means your coil is in equilibrium. Case 2. And we call this equilibrium as stable equilibrium. Next we have case 2. Case 2 says if magnetic moment is anti-parallel to magnetic field. If magnetic moment is anti-parallel to magnetic field, which means your magnetic field is in this direction. This is your magnetic field, and your magnetic moment is exactly in opposite direction. It's acting in this direction. So how much is alpha now? How much is alpha? Yes, 180 degree. Alpha is 180 degree. So torque comes out to be, it's mb sine 180. Sine 180 is 0, that means your torque is 0. This is again case of since net force is also 0. Whenever you place a coil in a uniform magnetic field, net force is always 0. So torque is 0, net force is 0, that means coil is in equilibrium. And this equilibrium is unstable. Now I'm not explaining stable and unstable again. We have done this plenty of time in chapter number 1 and 2. Okay, the last case, case 3. If coil is perpendicular to magnetic field, or not coil, magnetic moment. Okay, if magnetic moment is perpendicular to B, that means how much is alpha? How much is alpha now? Okay, what about theta in this case? How much is theta in this case? What about angle between plane of coil and magnetic field? How much is theta? You have relation between theta and alpha, right, Joanna? You're correct. Fatma, Joanna, what's the angle between theta and? If you have alpha, you can easily calculate theta. No, not 90. Yes, Joanna, 0. Theta plus alpha is 90. If your alpha is 90, that means theta is 0. That means plane of coil is parallel to magnetic field. So if this is your magnetic field and this is the plane of coil, this is the magnetic moment. Plane of coil is parallel to magnetic field, but magnetic moment is perpendicular. The torque in this case is mb sine 90. Sine 90 is 1, so this is torque mb. This is the case of maximum torque. In this case, your torque is maximum equal to mb. We also call this case as, if magnetic field is perpendicular to magnetic field, then this case is also known as case of radial magnetic field. We also call this as the case of radial magnetic field. That means your magnetic field is radial. First question on torque. Means alpha is 90 degree now. Field lines are in the plane of coil. That means magnetic moment is perpendicular. Your theta is 90 degree. Calculate first part. Net force on the coil. Net force on coil. Second, torque on the coil. Third, how much balancing torque should be applied on coil to prevent it from rotating. So this is a straight formula based numerical based on the same concept. Here you have a coil having n turns. The radius is given, current is given, then you have magnetic field. The first part says the net force on the coil. So the net force on a current carrying coil in a uniform magnetic field is 0. So answer of the part 1 is 0. For part 2, you first have to calculate the magnetic moment. Magnetic moment is NIA. So you have N, which is 25. You have I, which is 10. You need A, which is pi r square. Pi is 3.14 into r square. How much is r? R is 6 centimeter, which is 0.06 square. So this will be 3.14 3.14 into 36 into 10 raised to the power minus 4. So you can easily calculate your magnetic moment. It's N into I into A, which is 3.14 into 36 into 10 raised to the power minus 4. This much of ampere meter square. Now, once you have magnetic moment, you can easily calculate your torque. Your torque comes out to be Ni, not Nia. The torque comes out to be Mb sine alpha. You already have value of M. You know that your magnetic field is given as 1.2 Tesla. Your alpha is 90 degree. If I substitute all values here, let's simplify this expression. So that's 250. It's 36 into 3. If I, let's leave it as 3.14 into 36 into 10 raised power minus 4 ampere meter square. So that's M, which is 250 into 3.14 into 36 into 10 raised power minus 4 into B, which is 1.2 into sine. So this much of Newton meter is torque. There's one more part left. Okay, Fatma, if magnetic field is applying this much torque on the coil, and due to this torque, this coil is rotating, how much torque will you apply to prevent this coil from rotating? How much torque will you apply to prevent this coil from rotating? You will apply torque which is exactly equal to this torque. If a torque of 10 Newton meter is rotating the coil, then to stop the coil from rotating, you will apply the torque of 10 Newton meter only. You will apply same torque, but in opposite direction. Okay. Let's do one more numerical on the same concept. This is some 4.24 of NCRT. So a uniform magnetic field of some 3000 Gauss is established along Z direction. Gauss is the CGS unit of magnetic field along Z direction. A rectangular loop of side 10 centimeter and 5 centimeter, means length is 10, breadth is 5, carries a current of 12 ampere. It carries a current of 12 ampere. What is the torque on the loop in different cases shown in figure? What is force in each case? So we'll do two parts from this question. The first part, the diagram for the first part is This is your x-axis. This is y-axis. This is your third axis. This is part 2. Okay, in this question, he have changed the direction of axis. Like he's saying this is y-axis, this is x-axis, z-axis, and this is x-axis. Like x-axis is coming out of the plane. So whatever the answer you give will be according to this coordinate system which is given here. This is x-axis, this is y-axis, this is z-axis. Your first coil is placed in this way. It's carrying some current I. And this is your second coil. So this is 5 centimeter. This is 10 centimeter. Let's start with this thing. Okay, I'm solving part 2. You will solve part 1. Part 1 is easy. Part 2 is bit tricky. So this is your coil. First of all, calculate the area of the coil. What's the dimension? 10 by 5. Dimensions are 10 by 5. Is this the area? Okay, so 50 centimeters square. It's better if you can convert this in SI units. It's 50 into 10 raised to the power minus 4 meters square. That's your area. Your current is 12 ampere. Number of turns is not mentioned. That means number of turns is 1. You can calculate magnetic moment. That's NIA. N, which is 1. I is 12. Area is 50 into 10 raised to the power minus 4. Your magnetic moment comes out to be 6 into 10 raised to the power minus 2 ampere meter square. This is a magnetic moment, 6 into 10 raised power minus 2 ampere meter square. Okay, if this is your coil, this is the direction of current. Just apply right hand thumb rule over this coil and tell me the direction of magnetic moment. Okay, so for the direction, take your notebook, place your notebook in this way. X-axis, okay. Just place your notebook in this way, not in this way. This is your plane. Say x-axis is not outwards. So this is basically your usual z-axis. Your coil is an xy plane, means your coil is placed in this way, not in this way. Whatever answer you give is as per your axis, the axis given in the question. We're doing for part 1. Okay, I'm asking part 2. This one. Upwards. Fatma, this is anti-clock. This is clockwise. See, in part 2, take your notebook. Yes, now you are correct, Fatma. Take your notebook, place it in this way. Your current is moving clockwise, revolving clockwise. Just take your finger, curl it along the sense of current. Your thumb will be downwards. So the magnetic moment that I am using is 6 into 10 raised to the power minus 2. It's negative z-axis, which means minus of k cap ampere meter square. That's magnetic moment. After this magnetic moment, we can do one more thing. Magnetic field is 3000 Gauss. The direction of magnetic field is along z-axis. Right? It's along k cap. One Gauss is 10 raised to the power minus 4 Tesla. So it's better if you can convert this in terms of Tesla. 3000 into 10 raised power minus 4 k cap Tesla. So this is your B, which comes out to be 0.3 k cap Tesla. If I calculate torque, then torque is M cross B. You can solve it in two ways, either by direct cross product or you can use MB sine theta. I'm using direct cross product. So this is 6 into 10 raised to the power minus 2 minus k cap cross B, which is 0.3 k cap Newton meter. So this comes out to be, it's 6 into 10 raised to the power minus 2 into 0.3, this negative sign, and it's k cross k. It's k cross k. So this torque comes out to be, see, k cross k is 0. So torque comes out to be 0. Or if you want, you can solve it using this definition of cross product, that MB sine alpha. Can you guess the angle, the value of angle alpha in this case? Yes, 180. And how much is sine 180? Sine 180 is 0, so torque is 0. So you can either calculate your torque by this expression MB sine alpha, or you can directly take cross product and then calculate your torque tau equal to 0. So that's part 2, which I solved. Okay, look, now I'm solving this part 1. See, in part 1, area would be same. No, it won't be 0. I don't think it would be 0 in this case. Magnetic moment, the magnitude of magnetic moment is this, but what about the direction? What is the direction of magnetic moment in this case? What direction are you getting? Directions. Just write that direction what you're getting, I cap. Very good. Positive x-axis, not negative. It's not upwards, Jibena, it's outwards. See, this coil is now in the plane of your copy. This is in the plane of your copy. This placed in this way. Curl your finger along the plane of your copy. Your thumb will come outwards. Not upwards, outwards. Yes. Outwards means x-axis. The magnetic field is same. If I take M cross B, this will be I cross K. How much is I cross K? I cross K is J. So your torque comes out to be, it's 6 into 0.3 into 10 raised to the power minus 2 I cross K, which is minus J. I cross K is minus J. So 18, it's 1.8 into 10 raised power minus 2 minus J cap Newton meter. And as before, the net force is 0. So last topic of this chapter, which is moving coil galvanometer. So galvanometer is basically a device that we use to measure current. In fact, not to measure current, but to detect current or voltage. We don't really measure current or voltage using a galvanometer. We rather use it to detect current or voltage. So it's a device. Detect If you try to measure current and voltage using a galvanometer, then you will get a significant error. So we usually avoid to measure current and voltage using a galvanometer. We just need it to we use it to detect whether current or voltage are there or not in the circuit. The next is the principle of galvanometer. Principle is very simple. The principle says if you place a current carrying coil that we did in the last section, if I place a current carrying coil in a uniform magnetic field, then that current carrying coil will experience a torque. This is the principle of galvanometer. Current carrying coil This is the principle on which this moving coil galvanometer is based. Next, C, the construction of the galvanometer. Galvanometer have two magnetic poles. This is North Pole. And this is the South Pole. In between North Pole and South Pole, an iron core, a soft iron core is placed. This is basically a cylindrical core. You're looking at the top view over the system. That's why it seems spherical. It's not spherical, it's basically cylindrical, like this pen. On this soft iron core, this is basically a cylindrical core, turns of wire are wound over the coil. The turns are wounded lengthwise. Like if I take this pen, I'm not taking turns in this way. I'm rather taking turns in this way, lengthwise. This is the center of the coil. The magnetic field here is radial. The magnetic field here is radial. This is radial magnet. Radial magnetic field means magnetic field is always perpendicular to the plane of the coil. No matter how this coil rotates, the magnetic field will always be perpendicular to the plane of coil. It's along the radial direction. To generate these type of magnetic field, we are using concave pole pieces. So this is your soft iron core. Magnetic pole. These pole pieces are basically concave. This is magnetic field, which is radial, this one. This is radial magnetic field. Radial we did in case 3 of that torque on a current carrying coil. Radial means angle between magnetic field and magnetic movement is 90 degrees always. This is turns of coil. Then from this coil, we connected a spring. Like wire is, the coil means wire is wrapped around this cylinder. From one end of the wire is wrapped around the cylinder. From one end of the wire, I connected a spring. This blue color shows spring. This is basically a spring. One end of this spring is connected to the coil, so that if this coil rotates, then this spring will rotate. And another end of the spring is connected to a pointer. This pointer can move over the scale, and due to rotation of this pointer, you will get the reading. You can measure the reading using this pointer. So that's the construction. Okay. When you connect this galvanometer through a source of current, now when current I pass through galvanometer, or before is this thing, I'm defining some terms like N is number of turns. I here represent current through each turn. A is area of each turn. Then B is strength of magnetic field. Magnetic movement, here M is NIA. The magnetic movement of the system here is NIA. That's my first equation. So when current passes through this coil, this will experience a torque. When current I pass through this coil, it experiences a torque. And that torque is MB sine 90. Your angle alpha is 90 degree because field is radial. Field is radial. Which field? Magnetic field. So the magnetic field apply a torque MB over the coil. That's equation number 2. I can substitute 1 in 2. If I substitute 1 in 2, then it comes out to be tau is NIAB. That's equation number 3. Okay. Now we need a mechanism to stop this coil. See, this is a free coil. If you apply a torque over the coil, this coil will start rotating. This pointer will start rotating with the coil. It will not stop. You need a mechanism to stop this pointer. So to stop this pointer, I'm using a spring. And that mechanism is this spring basically. See, what's the property of spring? For spring, I'm defining this K. This K is torsional constant of spring. The torsional constant of the spring is K. This is K. Torsional constant means torque per unit twist. Torque per unit twist. Not just torque, but it's restoring torque. See, what happens in a spring is, if you take a spring, say this is your spring, okay? Instead of stretching or compressing this spring, you rotate this spring. What will happen if you take a spring and rotate that spring? As soon as you leave the spring, that spring will come to its original position. It's like if I take this thing as a spring, And if I rotate it and I leave, then after some time it will come back to its original position. This is what happens in spring. So when the spring come back to its original position, then a restoring torque is acting on the spring. Restoring torque means torque which takes spring back to its initial position. And this case for unit twist. Unit twist means if I rotate spring by 1 degree, then the restoring torque acting on the spring is K. If I rotate my spring by 2 degree, then the torque will be 2K, which will bring the spring back to its original position. If I rotate this spring by 3 degree, then it would be 3K. 5 degree, it would be 5K. So that is the restoring torque per unit twist acting on the spring. Is it clear? This term K. Are you getting this K? Sure. So due to magnetic field, this torque tau is acting. Magnetic field, or I should write this, due to torque of magnetic field, coil and hence spring will rotate by angle theta. Coil and hence spring will rotate by an angle theta. Then can you decide how much is the restoring torque? For unit rotation, restoring torque is K. For theta rotation, how much is restoring torque? Yeah, it would be K theta. That is equation number 4. That is equation number 4. So two torques are acting on the spring basically. One through the coil, which is trying to rotate this spring, and another the restoring torque, which is trying to stop this spring from rotation. So two torques are acting on the spring. One torque due to magnetic field, which is trying to rotate this spring. Another torque is this restoring torque, which is trying to stop this spring from rotation. What happened when this pointer stops in equilibrium of pointer? These two torques will balance each other. Which two torques? Torque due to magnetic field and that restoring torque. These two torques will balance each other. Torque, which is restoring, is equal to torque due to magnetic field. How much is your restoring torque? It's K theta. Torque due to magnetic field is NIAB. So you can write your I or your theta as NIAB by K. See, theta is directly proportional to I. Theta is deflection of galvanometer. So deflection is directly proportional to current, so it can measure current. Greater the current, greater would be the deflection of the pointer. So this is what you were supposed to prove, that deflection is directly proportional to current.